Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today my guest is from Mellanox. We have Todd Wilde. He's the Director of Technical Computing and HPC at the company. So Todd, welcome to the show today.
Thanks, Rich.
Hey, it's my pleasure. Thank you for coming on. I brought your slides up. Why don't we start with that, and we'll follow it with Q&A.
Okay, so hi everyone. I'm going to talk about Scalable HPC and new accelerations for high-performance parallel programming languages over InfiniBand. So Mellanox has introduced a new family of products that we call Scalable HPC. These offer the highest performing and most scalable parallel programming languages and libraries for high-performance computing. What we're doing with Scalable HPC is we've developed a couple different acceleration packages. One is called MXM, or Mellanox Messaging Accelerator, and the other is FCA, Mellanox Fabric Collectives Accelerator. And what we're doing is we're integrating these with various OpenMPIs as well as various commercial MPIs to make sure that you get good performance and scalability with those programming languages. The concepts of Scalable HPC really come out of a co-design strategy that we've implemented at Mellanox. If we look at the typical communication library and how it interfaces to the network, you have a network that really has been developed by hardware developers, and then you have the communication libraries that are basically being developed by software developers. Because of this, we see bottlenecks that can occur in the communication libraries. So the network's offering very high throughput, low latency, message rate, and hardware offloads, but the communication libraries may not necessarily be taking advantage of all of these offloads and efficiencies that the network offers. So this creates a bottleneck in the interface between the communication library and the network. So what Mellanox is doing with their co-design approach is we're bringing our expertise of the network and we're pushing that up into the communication libraries. So we're providing modules and routines for the parallel programming community to efficiently use the network through RDMA, through collective offloads, and various other accelerators that I'm going to talk about. So if I look at my typical MPI or SHMEM or PGAS architecture, which are all parallel programming libraries, these MPIs sit on top of the InfiniBand verbs, which is the API layer, into the InfiniBand network. What we're doing with our co-design architecture and with Scalable HPC is we're providing two different accelerators that actually get integrated into the MPI. One of these is Mellanox Messaging, which is we call MXM, and the other is Mellanox Collective Offloads, which we call FCA. So you can kind of think of this as two pieces. One handles the underlying send-receive messages and makes sure you get the best performance and scalability from those. And then the other package handles the collective communications, which are the communications that are run across all of the processes within an MPI job. So let's talk a little bit about these packages. The first I'm going to talk about is Mellanox Messaging. So Mellanox Messaging offers high performance and very good scalability for the underlying send-receive or put and get messages when we consider one-sided communications. The different things that MXM provides is, first, it provides properly management of the HCA resources and the memory structures within the HCA. We know best how to utilize the HCA and how to best efficiently set up its internal resources, and this is something that MXM gives us. It also has intra-node communication optimizations, and it has a hybrid transport technology for large-scale deployments. So depending on the size, we can select the best transport technology and the best transport protocol to run across the cluster. We also have efficient memory registration. It does the connection management and the receive side tag matching. And it fully utilizes all of our hardware offloads and capabilities that are part of the HCA. This package will be integrated with Mellanox OFED 2.0, and it's also available today as a standalone package. The other component is FCA, or Fabric Collectives Accelerations. This provides high performance and scalability for the collective operations that are part of the MPI job. Typical collective operations are synchronization operations where all of the processes in a job may wait to be synchronized at a particular point in the program, or something like a reduction where all of the processes are doing a sum of some value amongst all of them. But the key point is this collective operation happens with all of the processes taking part in the job. So FCA provides an acceleration of these collectives using a number of different features and techniques. The first of these is it's topology aware. And what I mean by that is it knows where all of the ranks reside within the fabric and how the networking structure is built with the fabric. So it can do optimizations based on where these ranks are placed within the network. It also takes advantage of the powerful multicast capabilities that are offered within InfiniBand. And it can run collectives on a completely separate service level so they don't interfere with other communications. Finally, FCA takes advantage of a technology that we have in our hardware called Mellanox Core Direct. This is a way to completely offload the collective operation to the HCA, so the CPU doesn't even need to do the collective. FCA incorporates this technology within it. As with MXM, FCA will be incorporated into Mellanox OFED 2.0, and it's available today as a standalone package. Both of these packages are available to run with our hardware, and they're basically downloadable on our website and free of charge. Today, FCA is supported by OpenMPI. It's supported in Platform MPI, and it's also supported in our SHMEM and UPC PGAS languages. And there'll be other MPIs that will soon be announcing support of FCA as well. I really wanted to take just a quick minute to show an example of how FCA can improve on the performance and the scalability within your cluster. I want to give an example of a collective operation without using FCA and then using FCA. So here's an example of an Allreduce. An Allreduce is basically some type of mathematical reduction. In this case, I'm going to do a sum of all the processes taking part of the collective. And then it's called Allreduce because the answer is actually then sent out to everybody that's part of the job. So typically, an Allreduce may be done using something called recursive doubling. How that works is I have 8 processes here, and each process pairs with another process to do the summation. So for instance, my core number 1 and 2 added up together to get 3, 3 and 4 added up together to get 7, and so on. So now I've gone from 8 to 4 processes taking place in the collective. Now I pair up again and I get 10 and 27, and I get my final answer of 37. Now the answer is on one machine, and that answer has to be sent to all the other machines so they have it. Okay, this is how it's done. This is a very small scale of only 8 processes. But as you expand on the number of processes, there's more and more stages that have to take place. So a 4,000 process Allreduce is actually going to use 12 stages to finish the recursive doubling algorithm. Now let's take a look at how we would do it with FCA. Remember, FCA is topology aware. So I wanted to show this example in terms of how the processes reside within the cluster. So in this example, I have 324 nodes named host 1 through host 324. Those hosts are hanging off of 18 different switches, so 18 hosts per switch on the level 1. And this is a 2-layer fabric to connect everything together. This is actually a fat tree InfiniBand fabric. I have 8 cores on each host. So I'm going to do the collective operation now, but since I'm topology aware, I'm going to do it in a way to minimize the amount of messages that cross the network and to optimize for performance. So first, I add all the numbers up within each node. So 1 through 8 were added up, and each node has its answer of 32. Now I'm going to pick a parent on each switch, and all of the other hosts on that particular switch will send their number 32 to him. This is what we call first-tier coalescing. You'll notice that there'll be no packets that'll have to go up to that second tier in this of switches in this first-tier coalescing. Now I have 18 switches that all have the answer 648. Now I'm going to pick a parent again, and all of the 18 other hosts that have their answer will send to that parent. This is our second-tier coalescing, and now I'm done. So I've taken a very large collective operation, and I've done it in only a couple stages. Now, to send the answer back, I used InfiniBand multicasting, which is actually a hardware replication inside my switches. So only one packet had to be sent up from host 324, and the switches then took over and multicasted and copied that packet to all the other hosts. So this is how we gain very good performance and efficiencies using FCA. As I said earlier, our mission is really to push out FCA and MXM to all of the MPIs and also some of the new PGAS languages that are being supported on InfiniBand. So we have it in MPI, we have it in a version of shared memory or SHMEM that Mellanox is providing, and also for a Berkeley UPC PGAS language that's becoming popular to run over InfiniBand. So all of these programming languages take advantage of our FCA and our MXM. I want to finish with just showing you a few performance slides, showing you the kind of the optimizations that we're seeing with FCA and MXM. This is a synchronization operation called Barrier. It's part of the IMB benchmark suite. Here you can see Barrier with and without FCA. This is a 256 process job. And you can see how FCA is scaling very nicely in the blue, while without FCA, with OpenMPI, we see much higher numbers in finishing our operation. I also have some barrier and reduce and broadcast numbers here for shared memory. This is on over 2,000 cores. You can see, let's just take an example of the barrier. It's very flat as it goes out. This is a good thing. This is showing scalability as we add more and more cores to the job. So you can see a 14 microsecond barrier when I incorporate FCA. MXM, as I said, is accelerating the underlying messages. A very good benchmark to tell that you're getting good performance with your messages is something called HPCC random ring. Here I'm showing random ring latency with OpenMPI out of the box, which is in the purple. I'm applying an optimization to OpenMPI called XRC, which is a new transport, or a more efficient transport at scale called ScalableRC. And then I'm running OpenMPI HPCC with MXM. And you can see the reduction I get there. This is on a fairly modest cluster of 16 nodes, 8 ppn, 8 processes per node. And I still see very, very good scalability and performance with MXM. That's all I had. Thanks, Rich, for giving me the opportunity to share this new technology with you.
Well, thanks, Todd. You know, I'm curious about as your roadmap goes forward, whatever's beyond FDR, I forget. I mean, how important will these technologies like FCA and MXM be to really achieving the potential of those faster networks?
So, yeah, we are shipping FDR today, and then our next technology will be EDR, which is 100 gigabits per second on a 4x port. These technologies are very important. What these technologies make sure of is a couple things. One is they allow you to scale and to be able to utilize those fast links in an efficient way. Also, as we get to larger and larger networks, things like server jitter or what you can call OS jitter have more and more effect on the collective operation. For instance, when you do a collective across all of the processes, you're only as good as your worst machine. So when you get OS jitter on these very large-scale networks, you know, the machine can take longer to complete the collective. With our FCA technology and actually offloading the collective to the HCA, we don't see those effects of OS jitter on the operation.
And then going forward, you guys have your technology where you can switch to the Ethernet protocol. Uh, are there similar kinds of things going on with performance that might benefit from these schemes, or is it a different way of approaching the problem?
Yeah, it's a good question. So our protocol that we use to be able to switch between InfiniBand and Ethernet is called VPI, or Virtual Protocol Interconnect. And with VPI, we can take advantage of a lot of the efficiencies that we were able to in InfiniBand on Ethernet. For instance, we can run the InfiniBand protocol over Ethernet. So there are pieces of this technology. For instance, a lot of the things we're doing in MXM could be applied to our VPI on Ethernet. But there's still advantages with InfiniBand, and things like the topology awareness of FCA are specific to InfiniBand, and are we were allowed to take advantage of it because of the InfiniBand topology and the feature set within InfiniBand.
Well,
so I guess the answer is some of these things will apply to Ethernet and some won't.
Sure. And then kind of a wrap-up question here, Todd. We've got the Sandy Bridge platforms are out there with the PCI Gen 3. How is Mellanox exploiting that platform to improve performance?
So you mentioned with Sandy Bridge the Gen 3 bus. If you actually look at the performance that you can get out of a Gen 3 by 8 bus, it's right around 56 gigabits per second. And that lines perfectly with our FDR technology. Our FDR technology can deliver true 56 gigabits per second across the wire. The encoding, we made some encoding optimizations with FDR, allowing us to get that true 56 gigabits. So we align very, very nicely with the PCI Express Gen 3 bus. If you really want to get the best performance on those Sandy bridges, and remember, many of those systems now are putting 16 cores behind the HCA. So we really feel like with the increase in cores on the Sandy Bridge systems that you need to have FDR throughput to be able to achieve the best performance for those cores.
Well, terrific. Well, Todd Wilde, I want to thank you once again for coming on the show today.
Thanks a lot for having me, Rich. I really appreciate it.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.